I think we can start. Some people join via YouTube also. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today we have Patrick Stengel from Jožef Stefan Institute, Ljubljana, Slovenia, and he's going to talk about mineral detection of neutrinos and dark matter. I'll send you a reminder when maybe 5 minutes are left.
Okay, thank you. And I'd like to thank the organizers for the invitation. So today I'm going to be talking to you about mineral detectors. So this is an idea I've been working on for 5 or 6 years now, more from a phenomenological perspective, but also sort of, as I'll talk about in the next few slides, just introducing sort of the topic, starting to get involved in some more experimental efforts as well to realize the potential of these detectors. But before I get to that, I'll say that while this was not our idea to look for new physics this way originally, it was sort of something that people had thought about and actually worked on preliminarily in the mid-90s. And then a few decades later, there was basically nothing, and we had started doing some more work on it just based on the advances in sort of the material science microscopy that's necessary to read out these sort of nanoscale or microscale signatures of nuclear recoil damage in ancient minerals. And so this was sort of the first paper in a long series of them that we had written about like 6 years ago now. And I have pictures of all of our co-authors. This was back when I was at Stockholm University working with the people you see here. And fast forward to the present. This is a paper from the second mineral detection of neutrinos and dark matter workshop meeting. This is sort of like a mini conference proceedings that followed a white paper that we had in the first meeting. I actually am going to Yokohama next week for the third meeting. So we're sort of rotating between the places where a lot of this work is centered. So it's a small group of, say, between 50 and 100 people, but there's probably about 12 different groups across North America, Europe, and Japan. And it's a fun project to get involved with because essentially you're bringing together people who are experts in astroparticle theory, like myself, along with the experimental side, people from neutrino physics and dark matter physics, as well as the geologists that you need to sort of give you knowledge about pulling the rocks out of the ground, and then the material scientists, as I mentioned before, who are experts in the technology to read out the damage from nuclear recoils. As I said, there's this mini proceedings that followed a much longer sort of white paper. So people who are interested can check out these two papers on the archive. And then after this next workshop, next week, sometime this summer, we'll probably have another kind of mini proceedings like this one. And sort of growing out of those meetings, people started putting together grant proposals. This is just one example that I'm a part of in collaboration with people in Switzerland and mainly in the US, coming from the National Science Foundation, basically to, it's one of these growing convergence research projects. And it's sort of exactly tailored to this kind of work where you're really incorporating expertise from different fields, from different places. So we have people in working on the imaging that I'll talk about today in different methods. So for the sort of like nanoscale electron microscopy and atom force microscopy, things like that, there's people at the University of Michigan and University of North Florida. Then also there's this sort of lower resolution but higher throughput kind of techniques that's people in the Paleocene collaboration, which mainly involves myself, people in Virginia Tech, and at the University of Zurich. And then finally, there's some people working on X-ray imaging for this, also at the University of Michigan and at SLAC, and a few other places. We also have experts in geology from the University of Maryland and Syracuse, and then people working more on the phenomenological end, including people in Texas and North Florida. So the point is that this has sort of grown in a short number of years. I think it's fair to say that some of the early phenomenology work that I did with my collaborators sort of has sparked this, and then we've sort of pushed it along to get to the point where there's some real funding to try and realize the potential that I'll talk about in my talk today. So I'll start with just applications of these mineral detectors in particular. I'll mainly focus on dark matter as an application, but of course, astrophysical neutrinos are backgrounds for dark matter searches, but they're also interesting signals in their own right. So I'll briefly talk about a few of those applications before moving on to dark matter. Then I'll say a bit more specifically about some of the readout technologies that we're using to make these detectors, and then show some projected sensitivity for dark matter searches. So if you think about dark matter experiments, the kind of neutrino backgrounds that you are worried about include atmospheric neutrinos, which just come from cosmic rays interacting in the Earth's atmosphere. They make these particle showers, which eventually your mesons decay into leptons. You make a lot of neutrinos in the end of this, and those give you some background for your coherent scattering in your dark matter detector. So one interesting aspect that is if you have a sample that's, say, 100 million years old, right? You're not just measuring the atmospheric neutrino flux now, you're measuring it going back across that amount of time. And so all of the different sort of physical systems that are incorporated into the atmospheric neutrino flux, you can sort of, if you have, say, a detector every 100 million years going back a giga-year, you can get sort of this coarse-grained picture of how these systems are evolving. And so that, of course, includes the source, which is just the cosmic ray intensity sort of locally at our part of the galaxy. Also, you're getting some measure of the evolution of the Earth's atmosphere, which is the target. So both its composition and density that could have changed over these time scales, and that's interesting more broadly, not just for physics. Also, something that's a little bit more cross-disciplinary is the Earth's geomagnetic field. Of course, that puts some low energy cutoff due to the deflection of cosmic rays coming towards the atmosphere. And if that has changed in any significant way over the last billion years or so, you can measure those kinds of effects. Sort of going down in neutrino energy, the next thing you think about is core collapse supernovae. And so the only thing that's been sort of measured in neutrinos is an event like 1987A. And those are expected to happen only 2 times per century. So I guess we're due for another one. But the point is, if you're building a real-time detector, you have to sort of sit and wait. And this is a very long time scale. Of course, if you have a detector that's 100 million years old, right, you're going to actually have quite a lot of these events giving you neutrinos. And so you can measure across these sort of long time scales. You can see in the plot down on the right the evolution of the core collapse supernova rate. So basically on these very long time scales, say 100 million years, these stars are being born at the same rate that they're dying. And so what you're really measuring is the star formation rate in the galaxy, if you're, again, sort of measuring the evolution of this over some amount of time. Of course, we can't really go back the full extent of this plot. You could only really get some sort of measurement on, say, like where the red dot here is sort of randomly on this plot if you go back like 1 billion years. But the point is, you sort of get to look outside of your light cone, as someone once said, is the way to think about this. So usually when you're measuring the core collapse supernova rate, it's the diffuse rate happening outside of the galaxy, right? But if you have a detector that's 100 million years old, right, the flux coming from inside of the galaxy is actually larger, essentially because it's not just one of them happening well, they are happening every 100 years, but it's not a singular event, right? It's something that's happening um, closer to you and at the same rate as things outside of the galaxy. So that's actually what you observe rather than the diffuse rate. And finally, down even lower in energy, you have things like solar neutrinos. And so the fusion chains on the left give you some of the neutrino fluxes you can see in the plot on the top right. And the historical evolution over geological time scales for this flux is also of interest. So you can see how some of these fluxes are expected to evolve in time in the plot on the bottom right. And this information could be interesting because there's different ideas about competing models for how the standard solar model and the metallicity model in particular can work. And some of these fluxes have different temperature and thus time dependencies, and mineral detectors could be one interesting way of trying to pick these things apart in a way that you couldn't do with a conventional sort of real-time experiment. Okay, but now I'll just give a brief introduction to dark matter, since that's the application I'll be focused most on today. And so there's evidence for the existence of dark matter at a variety of scales and epochs. The two pictures here are sort of focused on galaxy and galaxy cluster scales. I'm sure many of you have seen these pictures before. But just to summarize, so the plot on the left is showing a galactic rotation curve. The black dots are the data of the stars in some nearby galaxy that we observe. And you can see that that rotation curve is flat. If that galaxy was made completely out of baryonic matter, you would expect the rotation curve to look like the long dashed line that's sort of falling off due to the just gravitational interactions between the matter that you can see. But if you had sort of a puffy halo of dark matter that encloses all of those stars, you get a contribution that looks like the dot dash line. And it's the sum of those two that gives you this sort of flat rotation curve and tells you that either you need some kind of dark matter component, or alternatively, you could also get this kind of rotation curve with some modification of gravity on those scales. But then that brings us to sort of the picture on the right, which is a picture of the bullet cluster. This is a composite image coming from the Hubble Space Telescope. Chandra X-ray emission is shown in the sort of red clouds here, and the gravitational lensing, where the mass is in these, it's actually two galaxy clusters, is in blue. And so the fact that the sort of center of mass, where the mass is in the galaxy in blue, is different from where the baryonic emission, so where the X-rays are coming from, in red, is telling you that there's some collisionless component that's giving you sort of most of the mass in these galaxy clusters that's not giving off any light. And so while people have different kinds of explanations to, say, modify gravity to give you the picture on the left, it's harder to replicate for the picture on the right. There's additional scales where there's evidence for dark matter, including all the way up to the CMB, large scale structure, etc. But these are sort of the scales that are more relevant for dark matter detection, which I'll talk about today, direct detection. And so based on these sorts of observations, you get a very basic list, although theorists like myself will give you a bunch of different little workarounds to any one of these. But just as a basic explanation, set of assumptions, you would say that there's no electromagnetic interactions, so the matter is dark. Also, it must be cold and stable in order to form the kinds of gravitationally bound structures that we observe in the galaxy today. And if you take these first two assumptions, that sort of leads you right into the third one, which is that there's nothing in the standard model that can satisfy these kinds of constraints. And so the sort of observational evidence of gravitational dark matter interactions is one of the best motivations for new physics that we have today. And so the cartoon on the right is showing you different ways that you can look for what I'll focus on today, which is sort of WIMP dark matter, which I'll talk about more in a second. But basically, if you have dark matter that's roughly the same mass as atomic nuclei, it has weak scale or same ballpark as weak scale kinds of interactions. You can detect it these three different ways. In particular, if dark matter was produced by self-annihilations in the early universe, you can look at places where you know there's a high dark matter density today and detect the standard model byproduct of those annihilations through indirect detection using some sort of space-based or ground-based detector to look for photons, neutrinos, what have you. You can also think about reversing that process. So taking standard model particles and making dark matter, that's something like the Large Hadron Collider, in which if you make some dark matter particles in your final state, they'll just sort of escape the detector. And what you'll measure is missing energy in a way that's not accountable to neutrinos or something else that you don't measure inside of your detector. But what I'll focus on today is direct detection. And so if you either have a conventional direct detector that's buried underneath the Earth due to cosmogenic backgrounds, which I'll talk about a little bit later, or a mineral detector in some borehole. Because of the weak interactions of dark matter, the Earth is transparent to it, and every once in a while, the flux of dark matter crossing your detector will interact with the target and allow you to try and measure it. And so the plot on the bottom left is showing sort of the very basic kind of theory parameter space. And the point of plots like this, which is from the Snowmass paper on dark matter, I think, is basically to say that when you see this sort of two-dimensional parameter space with dark matter mass and interaction strength, you can ask a theorist and they will give you some theory which puts you anywhere in this plot over, say, 19 orders of magnitude on the mass axis and a similarly large 20 to 30 orders of magnitude on the interaction strength axis. But what I'll sort of narrow down and focus on today, again, is the idea of this thermal WIMP, which are these light blue kinds of ovals that you see, in particular WIMPs that are heavier than sort of GeV kind of masses, which has been a sort of typical area of focus for the kinds of searches you see on the cartoon on the right side. So the way a conventional direct detection experiment works is you have something like LZ, which is a dual phase liquid xenon TPC. And the two phases are if you have something like a WIMP coming in, it hits one of your xenon atoms, and that will give you some fluorescence light that's detected by PMTs on either end of your detector. Also, the recoil of that xenon atom will create ionization electrons that can then be drifted by a weak electric field up to the gaseous phase of the TPC, closer to the PMTs, and then give you more light. And it's the combination of these two signals that gives you this sort of good signal background rejection you need to do these rare event searches. And just to consider what the kinematics are for searches like this, the plot on the top right shows the nuclear recoil energy as a function of target mass for a variety of different incoming WIMP masses, or the different colored lines. And this is assuming relative WIMP velocity of around 100 kilometers per second, which is just sort of typical velocity you expect in our part of the galaxy. And you can see that if you have something like a xenon atom, right, the target mass is somewhere closer to 100 GeV, then the recoil energies you expect go from sort of some tens of electron volts up to, say, tens of kiloelectron volts. So these are the kind of really low energy nuclear recoils you need to be able to measure in order to detect dark matter like this. And so starting with some particle physics model, you fold in the structure of nucleons and the nuclei in which they reside. You also fold in the WIMP flux that you expect to see based on observations like the ones I showed a few slides ago. And then the sensitivity you have, given all of that, is really controlled by the product of the number of target nuclei that you have multiplied by the exposure. And so for a conventional experiment, what they're really trying to do is maximize the number of targets by building larger and larger instrumented volumes of, in this case, liquid noble gas, in order to be more exposed to rare events. What a mineral detector does is it sort of turns to the second factor, which is just the exposure time. So even if you only have the number of targets equivalent to, say, a gram of material, if that material is 100 million or a billion years old, you can really get quite a lot of exposure. One way to think about it is 1 gram gigayear, if you move the zeros around, is equal to a kiloton year. And so 100 of those is like the exposure of super K, but with a nuclear recoil detection threshold, something closer to these liquid xenon TPCs. It doesn't come for free. There's a lot of backgrounds, which I'll get to, but that's the basic story where mineral detectors can be useful. Okay, so now I'll talk a little bit about some sort of going back in time, just to sort of set the stage a little bit about solid-state track detectors, and then I'll discuss more recent efforts in the last couple of years that I mentioned before, that I'm involved with in more or less official ways. And then I'll discuss some backgrounds that are in addition to the neutrinos that I already mentioned before. So solid-state track detectors are a fairly old idea, maybe going back 60 years or more. And the first thing that people looked at were fission tracks in mica. So the picture on the left is a TEM micrograph, just showing what you get when you have a spontaneous fission of something like uranium-238. You get a fission byproduct that's about half of the mass of the original atom. You get 2 of those. They fly away back to back, more or less, with some tens of MeV in energy, sort of right on the Bragg peak where those particles are in this material. And that leaves these really sort of like long, compared to what I'll talk about, tracks that deposit lots of energy in your material. And so the picture on the left is just TEM. You can see the length scale down at the bottom. And so this is without any sort of like etching or preparation of the sample, besides just mica has this nice property where along one of its principal directions, it basically is able to be peeled off in 2D slices, which are useful for TEM images. But they also figured out that you can use optical microscopy, which is what is shown on the right, if you use a chemical etchant. So it's some kind of acid, at least in this older, very established ways of doing this now, where the etchant attacks all of the material in your sample, but it just sort of eats away at these tracks more than everything else. such that, again, you can see the length scale changing. You can measure sort of just even with an optical microscope these fission tracks in the same kind of mica material. So using these kinds of techniques go forward like 30 years. I mentioned this a little bit earlier. And using atom force microscopy, which I'll mention a little bit in the next few slides, or sort of more modern version of that. It's different from electron microscopy or optical microscopy. Atom force microscopy is basically if you just have a really sensitive needle that moves in a rasterized pattern across a two-dimensional surface. It's able to measure nanoscale or even sub-nanometer precision, sort of the depth of that material. And so if you have these 2D surfaces and do some chemical etching that enhance the size of the damage, the depth of these etch pits is telling you something about the recoil energy. And it's these two things put together that allow basically you have nanoscale precision and etching that let you be sensitive to these sort of KUV scale nuclear recoils and much lower charged nuclei. And so the plot on the left, in particular the calibration, which is the lower panel, is showing basically if you take a piece of mica, you put it next to a californium source, the neutrons that you get from that source will sort of replicate the kinds of recoil energies that you expect to see from a WIMP. In particular, there's some Monte Carlo shown in the dashed line, and then the neutrons they observed are in the solid line. And again, you sort of think of lower summed etch depth or lower track length, right? These are all sort of proxies for the recoil energy. And so you expect this sort of like, at least for the canonical kinds of WIMP interactions that we think about, these kinds of spectra to peak at lower energies or lower track length or etch depth. And that's kind of what you see here for the neutron calibration. And then when they go to their natural sample, which is the top panel, they basically say, okay, we have these alpha recoil backgrounds, which I'll talk about more in the next few slides. But if you look at sort of the lowest bin, where they know they're sensitive, given their technique and the calibration, they don't see any events. And so it's that lack of seeing events that allows them to set the kinds of limits that you see in the plot on the right-hand side. So this is the same plane as I showed the sort of cartoon with all the theories on it. But this is now basically these kinds of plots are common in direct detection, where everything above this line, so a WIMP of a given mass with that cross section or higher, is excluded. And so you're starting to dig into this parameter space, and these limits were close to competitive with some of the original conventional direct detection experiments back in the mid-90s. I think experiments like CDMS and these germanium detectors were just sort of getting going. But now, as I'll show, the sensitivity of those conventional experiments has gotten much, much better. And so the kind of technology advances you need on the mineral detection side have taken some time to catch up. And that's what I'll be talking about a bit more later. In particular, I'll show something that's sort of the sort of ongoing experiment that's closest to the Snowden et al. Experiments from 30 years ago. And this is ongoing at Jamstack in Yokohama, where our meeting is next week. And this is taking the same idea as AFM, where you make some tracks. You have mica, which is this cleavable material, along certain directions. You etch it to get these pits, which are some nanoscale in depth and can be micron sized in width. And rather than having an AFM, which is traditional sort of functioning, just has an actual needle, you can use these what are called optical profilometers. I believe I'm saying that correctly. Which rather than having a needle, it actually just has a laser that is able to measure these sort of nanoscale changes in surface height much more quickly. and have automated sort of analysis instead of having to go through these sort of individual micrographs just by eye to find these pits. And while this doesn't recover all of the sensitivity between, say, where conventional direct detection experiments were in the mid-90s and where they are now, which I would say is about 10 orders of magnitude in cross section, give or take. This does get you like a factor of 1 million throughput that's possible with these experiments. And so in sort of log space, it's getting you halfway there. There are plans to scale this up. In particular, these are pictures from some of the calibrations. So the way these different panels work is going left to right, you have heavier, like higher Z nuclei. And then going top to bottom, you have sort of a factor of 10 in energy, right? So top left is sort of the lowest ionizing, and bottom right is the highest ionizing, which you can see by the stopping powers as well. And so for the low ionizing particles, which are reminiscent of what you would get for dark matter nuclear recoil, you can see that there's some efficiency where you don't, if you are counting all of the ions that you're, sorry, my headphones are dying. I gotta switch to my.
Sorry, is there any problem?
Yeah, my microphone and my headphones are dying, so I have to. Sorry. Can you hear me?
Yes.
Okay. Sorry. Yeah, the earphones were dying, so it was also their microphone, so I had to. Okay. Sorry about that. And so taking into account these kinds of efficiency factors, and with the sort of automated scanning process, you can go through again, like the amount of area you're able to scan. It really is just, it's orders of magnitude larger. And so while this doesn't get you all of the way, maybe in some combination with some of these other techniques I've talked about, you can really start to be competitive in sensitivity with conventional experiments. So this is from the Paleocene collaboration, this particular technique, which is called light sheet microscopy. This is also part of the NSF grant I was mentioning earlier. There's a lot of overlap with that as well, along with these different institutions. But the idea here is it's an optical technique. And if you have a certain kinds of transparent materials, um, low energy nuclear recoils will create some vacancy, which an electron can fall into. If you kick out a nucleus, an electron falls in. And so clusters of these anionic vacancies give you this quantum mechanical effect such that if you shine white light through your material, that light will get absorbed by these color centers and then emitted at some specific wavelength. And so in this way, even with an optical microscope, which says, say, micron level precision, you're able to measure even these single vacancy sites very, very quickly, right? So you have optical sort of scanning speed with nanoscale physics going on. Of course, you lose some amount of resolution in that process, but the idea is, at the very least, you could take this kind of technique and use it to look at some larger crystal, right? And find some interesting areas where there's some potential interesting events where you want to zoom in with some of these other techniques that I'll talk about. Because the value of this is that you can really look through very large samples very quickly. I think for a gram or in spatial dimensions, centimeter cube size sample, we should eventually be able to scan that in just a few hours. And so that's really a game changer in terms of the throughput that you need to do these kinds of studies. So you can see the way the microscope works in the bottom panels. So there's just some sample mount that has just they're very advanced sort of just cameras that are looking at the sample, and then in the bottom right you can see the light sheet sort of in these planes working through the sample and giving you this effective 3D image as you go through in Z. And so this was a paper that just came out in the last month or two. It's the first sort of physics result from the Paleocene collaboration that I think is really interesting. So we wanted to be able to image some sort of physics going on inside of the bulk of the material, so not something that's on the surface. So if you have sort of this centimeter cube size sample, you don't want to have to take it apart or anything. You want to just be able to scan through it is the idea. And so in order to do that, we were looking at lithium fluoride, and one interesting process that sort of was the best sort of proof of concept for this idea was actually just the fission of lithium-6, which exists in lithium fluoride in some sort of percent level abundance. But if you have thermal neutron capture on lithium-6, it'll make an alpha and a tritium, each with a couple MeV in energy. And these are very, very low ionizing particles, right? And so even though they have this sort of high energy, which makes them travel, say, some tens of microns in the material, the amount of damage they're doing from ionization losses, for instance, is basically negligible. And so the only way to really see these is with a technique like this one. And the picture on the left is showing one of these events. So you can see basically with the ranges you expect, the alpha and the tritium back to back. You can even see we have some we still have to quantify how well it does, but we have some measure of DEDX. Basically, you can see on the bottom right is where the alpha is, because that's creating many more kinds of vacancies than the tritium track, which is on the upper left. Okay, and these things flying away back to back is again roughly the length that you expect. And so we're sort of seeing the Bragg peak where as you get towards the end of these tracks, the nuclear scattering cross sections are going up as the energy of the ion goes down. And so that's where you're getting these sort of bright ends, but also you have some of these color centers in the middle. I should also say this is a Z stack, right? So this is combining a bunch of different planes in Z together onto a 2D projection. And so the plot on the right is showing the bulk of the material that we were looking at in the paper. And so inside of this volume, which is say about 500 by 500 microns in X and Y, which is the plane that you're looking at. This also goes a couple hundred microns in Z. I think there's about 10 Z planes in this picture. I'm not exactly sure of that number. But the point is, given that volume and the sort of fluence that we were, of thermal neutrons that we were sending in and the reaction rates, there are about 5 to 10 of these sort of double bright end thermal neutron capture events in this picture. Everything else is some kind of other neutron recoil, or we also saw some things that definitely corresponded to cosmogenics, which are probably the brightest things that we see here. But the point is that using these kinds of techniques, you can find these really, really low ionizing tracks inside the bulk effectively in 3 dimensions. And like I said, you can these pictures took a couple of these particular samples took a few days to make to do the scans, but with a lower noise camera and some of the improvements that we're making, realistically, doing these kinds of samples is possible in a few hours. So, switching to a couple of other techniques that we talk about more in the phenomenology papers. Um, in particular, this was like 5 or 6 years ago when we were just a bunch of astroparticle theorists guessing at how microscopes work, essentially. I mean, we consulted with people and talked to them about this stuff. But the way to think about these two techniques, I think, is more as like proxies for techniques that have the same kind of possibility for throughput and resolution, even if they're not the exact techniques that people actually ended up using. But the idea for sort of higher resolution with lower throughput, so say like nanoscale resolution, like an AFM or this optical profilometry, this was helium ion beam microscopy. So this is basically doing something like electron microscopy, but with helium ions rather than electrons. That has several advantages. In particular, you can get some subsurface kinds of imaging, and you can combine it with pulsed laser ablation so that you're effectively like alternating between imaging and kind of blasting away the layer that you just imaged. And you sort of do this serially to read out the sample. While this technique is possible and people have shown that it works before. Of course, you're destroying your sample just manifestly as you go. And so it's not kind of ideal. And I think some of these other techniques at the nanoscale are more promising. Something a little bit closer to um, what we started working on with people at SLAC in particular is this small angle X-ray scattering. And so this is if you have a synchrotron light source, you basically can map out the electron density using pyrography, where you have your sample on some stage that rotates. And again, you're sort of assembling this collection of diffraction patterns from a bunch of 2D images to make these sort of three-dimensional reconstructions. And so the picture on the bottom is some artificial glass that was grown in a lab that sort of demonstrated that you can get this kind of 15 nanometer, now sort of going even further down towards like 10 nanometer precision in 3 dimensions for much larger samples, sort of at this 100-gram scale. And importantly, without a lot of the sample preparation, that was essentially
Hello? Yeah, we have
yeah,
5 minutes left.
okay, that was essentially a significant bottleneck on the um, sort of sensitivity of these earlier studies. So I'll skip ahead to the backgrounds. And so, like I mentioned before, there are cosmogenic backgrounds that are important for any sort of dark matter experiment. In particular, in the kind of units that we care about, right, which are a little bit different than what we normally think about for dark matter experiments. We only really want like a centimeter of material, but that centimeter has been sitting there for a gigayear. And so you can see the cosmogenic neutron flux as a function of sample depth, right? And by the time you get to 5 or 6 kilometers, the neutrons you get from the muon flux, which is shielded by the overburden of the Earth, so it drops below 100. And relative to conventional experiments, because of the radiogenic backgrounds, which I'll talk about on the next slide, these sort of like 100 extra events that you have are really nothing compared to the sort of tens of thousands of signal events plus background, or hundreds of thousands, depending on the exposure that you expect to have in mineral detectors. So something like 100 or a few hundred background events really isn't going to impact your sensitivity in a meaningful way. That being said, if the controlling backgrounds are coming from radiogenics, you have to consider the radioactivity in your material. And if you just pull some random rock out of the earth, it's going to have sort of parts per million uranium-238 concentrations. And so you need much more radio pure, or rocks forming in much more radio pure environments than that. And those are the ones that we are looking into, namely marine evaporites and ultra basic rocks. And for those, you basically get suppressed backgrounds coming from just alpha recoils, which I mentioned before, where you have this sort of tens of keV recoil of a very heavy nucleus, but this happens in big clusters because over these long time scales, essentially you're getting the full uranium-238 decay chain. The harder thing is the neutrons that you get from things like spontaneous fission, which without any sort of active or passive background rejection are just going to downscatter in your material. And you have to see what your sensitivity is after you count them. And so what you wind up with after putting all of that together is a picture like this one, which is showing the track length spectrum as a function of track length rather than sort of the recoil energy spectrum as a function of nuclear recoil energy, which is the way these sort of plots usually look for conventional experiments. And blue, you can see the low mass dark matter benchmark, and that's competing mainly with things like solar neutrino backgrounds, which I mentioned before. Whereas when you have these heavier WIMPs, 500 GeV WIMPs, really the hardest thing out past all of the neutrinos, which you see in black, are this orange curve that's dotted and dashed, and that's coming from the radiogenic neutrons. And so this is the comparison to existing direct detection searches. This plot's from the white paper, which is a couple of years old, so the gray region should be going down a little further. But this is showing what you get in the high exposure case. So this is like a 100-gram sample with 15 nanometer resolution. In the high resolution case, which is nanoscale resolution with a 10 milligram sample, you can see that you have this typical trade-off that you get in direct detection experiments where the high exposure case can push down a little bit more at high WIMP masses away from the threshold of the detector, potentially competitive with current dual phase TPC experiments that I mentioned earlier. But where this kind of technique can really be powerful is in the high resolution case, basically where you can get down to the neutrino floor for something like a few GeV WIMP. In a way that will be difficult even for next generation sort of cryogenic bolometer experiments. So I hope I've convinced you that mineral detectors can look for these rare events like dark matter and neutrinos, and that there's particular kinds of phenomenology that are very interesting when you can sort of go back over these geological timescales. As I mentioned, there are a bunch of different groups that are now working on primarily the sort of track reconstruction, the imaging aspects of these detectors to find out what works for different kinds of signals. And something that I'm particularly interested in is the sort of data analysis you need to do in order to take these sort of nanoscale features imaged inside of a centimeter size volume and sift through everything with all of these backgrounds and find the tracks that you want. Thank you.
Okay, thank you for